So I'm glad we got through the basic math stuff we needed. That was necessary, and it will help a lot down the road. Probably a little bit soon you'll see it help. Okay? And it'll help us in general to save some time this year, so we don't have to go back and reteach that kind of stuff. So in chapter 2, we start to talk about the motion of an object in one dimension, which you talked about already last year. You talked about 1D kinematics, where an object is only moving left to right, or an object is only moving up and down. Those are the two scenarios that we look at for one-dimensional motion. Remember, an object moving like this is not one-dimensional, right? At an angle because we're moving in the y and the x direction. Don't confuse one-dimensional with an object moving along a line. Because an object moves along a line like this because gravity is an effect. An object moving up and down moves along one line because gravity does affect it, but only vertically. But the minute an object moves like this, you might be tempted to say, oh, it's moving along a straight line. And if it's like downward angles, well, it's a little bit different there. Okay, so we're going to talk about at angles versus one-dimensional. We kind of have to start with one-dimensional, but the idea behind this is that we're not going to like redo everything you did last year. It's a waste of your time. So what we're going to do is I'm going to introduce the formulas we've seen in the past, and then we're going to jump into where the calculus is involved in these formulas. For the most part, this text uses a lot of derivatives and a lot of integrals. You haven't done things with integrals yet in calc, but I'll start to give you the idea behind what an integral is, because it is used in the beginning of this text. But the derivative is something you do know already, and what I'll do in the beginning is I'll stick to functions that are polynomials for now, because you guys have been doing the power rule, right? Have you done quotient, product, any of that other extra stuff, or has it just been power right now? Any other rules or derivatives besides power?
We haven't done any rules yet.
You don't have.
We did power
And the dot thing.
the dot product.
Or the dot product. That was this.
We did the sum and difference rule and the
Dot product, we didn't hear.
we did the sum and difference rule.
Okay.
It's
Is this we did scalar, multiple rule, sum and difference.
Sorry, so Matt, you're right. You guys also did something we call dot scalar product, right?
We did the scalar, multiple, and then sum difference.
Rule. Oh yeah. Okay.
Sum and difference, yeah, for not vectors, but for for derivatives. Got it. All right. So with that said, what I'm saying is I will keep our functions to polynomials for now. So when we do the derivative, it makes sense. And then once you get those other rules down pat, we're starting to get into those. So let's go over some general stuff real quick. And again, I'm going to introduce ideas first, and we're going to get into the calc of it. So the first idea is the concept of position and displacement. The position of an object is its location at a given time. The position is its location at a given time. The displacement is different. Displacement is different than position, although they're very much interchangeably used. Remember, displacement is the change in an object's position, which is its final position minus its initial position. Now, your textbook doesn't use I and F. The nomenclature, if I'm correct, let me take a look. Yeah, the nomenclature it's going to use is going to be just 1 and 2, or simply putting delta and not using I and F. So it's the same thing as this. Okay, x2 minus x1. But you usually, or in physics, we talk about the final minus the initial. So although it's not going to be used as xf and xi, that's how we think of x2 and x1. So again, this is displacement here. This is an object's displacement. And displacement we can think of as a change in position. So position is an object's location at a given time. Where displacement is the change in that position. The change in that position. Now, in general, this is stuff that I have to just quickly reiterate, but I think you should know this by now. In general, we consider 0 on a number line, and then we consider to the right to be positive displacement, and we consider to the left to be negative displacement. So if an object started here and it moved left, we would say that it's negative displacement. If an object started here and it moved right, we would say that's positive displacement. Displacement is what kind of quantity? What kind of quantity? A vector quantity. And how did you know I was asking about being a vector? How did you know I was referring to it being a vector?
Magnitude and direction.
Okay, it has a magnitude, the magnitude being the difference between these two quantities, and the direction being the way it moves, either negative or positive. Position has a positive or negative sign also. Position has a positive or negative sign also, depending upon where it is. Okay, so to quickly go over some stuff again that you've done last year, and I'm skipping stuff, I promise. We're not doing all the stuff in this text. So I'm jumping through section 2.1 right now. The second formula you learned last year was that your velocity on average was equal to the change in position over the time period elapsed. Average velocity was the change in position or your displacement over the time period elapsed. So we could say this is x2 minus x1 over t2 minus t1. And you already did this. When did you just do this?
Last night.
Yeah, in your lab. Whenever you finish your lab for this, and you were calculating the average velocity of this particle, or you, or the object you slid down a ramp, or whatever the apparatus was you used, you calculated the initial and final position over, the difference in initial and final position over the difference in initial and final time, or final initial time, and final initial position. But in the correct order. So if I were, for some reason, switch these two, I could technically switch those two and I still get the same answer. It's like slope, as long as you're consistent amongst your variables. Now, again, this is average velocity, average velocity. How does this differ from average speed? How does this differ from average speed?
Average speed would be the absolute value.
Close. Sometimes, yes. To answer that question, sometimes that will work. Not always. I'll get into that in a second. We could use absolute value in certain times. What is the general formula for average speed? I know I talked about it last year in my class. Pretty sure you talked about it in the other class. We must have talked about it for average speed. How does speed and velocity differ? And I know sometimes it's absolute value. We'll get into that.
Velocity is a vector and speed is scalar.
Okay, good point right there. That's a good starting point. That'll help.
Is it just delta x over t?
That would give us the velocity, delta x over delta t. Yep, it's the velocity. But I'm asking about speed.
Speed is distance over time.
Remember, speed is distance, not displacement. Let's make sure to write that down here. Oops.
So the distance would be positive, right? Yeah.
So, as Spence said, if you were only moving in one direction, then your speed is the absolute value of your velocity. So let's take a look at the sample. I'm walking across the room at 1 meter per second. That's my velocity. My speed is also 1 meter per second right now. But the minute I turn around and do this, now my velocity is the change in my displacement. I started where that black marker is. I ended where the red marker was. So my average velocity would be this displacement, which is a positive displacement, divided by the time it took me to do that. That's going to be my displacement. But my distance traveled will be, I'm going to set 1, 2, 3, 4 steps, 5, 6 steps, or 6 meters of distance, 4 that way and 2 back over the time period. So again, distance is not the same thing as displacement. This distance is the sum of all your displacements, where it goes from I equals 1 to, I guess, k would be the way to write this. Max, you could probably help me if I'm taking calc right. I forget the nomenclature. If you go from like I equals 1 to k, of all your little displacements, absolute value together sum. Okay, that might not be the right way to write it. I'm trying to give you guys notation so you get an idea though. So imagine all of your displacements from I equals 1 to k, meaning however many displacements you have. In that case, we had 2 of them. Absolute value summed together. So for the example I just gave of walking 4 meters to the right and then 2 meters back, if I were to calculate these two values, and let's say it took me 5 seconds to do this, if I wanted my average velocity, my answer would just be 2 meters over 5 seconds, or simply 2/5, or 0.4 meters per second. while my distance over time, or my average speed, would be a total of 6 meters over 5 seconds, which equals 1.2 meters per second. So again, where does the 6 come from? 4 and 2 added together gives me the total distance, which is what I'm trying to show right here. You sum together all the little pieces of displacement over time. Questions on speed versus velocity? On speed versus velocity? We're definitely going to use it. You are already ahead of the curve in calc, because in calc you're going to talk about speed versus velocity, or distance versus displacement, and you're going to learn about integration later, and you're going to have to know the difference between the two. Okay, so this is a very important thing for both courses. Average velocity, average speed. So what could you tell me in general? Can we make some sort of conclusion about speed and velocity and their relative comparison and their relative magnitudes? What could you tell me?
I don't know, like how to use it though.
It's okay. What would you tell me in words?
Like speed is the average of how fast the object's moving in total, and then velocity is like the average of how fast it's moving in a set direction.
Okay, the first part works. Speed is the average of the speed you're moving through the whole thing, doesn't have direction. How about their magnitudes though? The relative quantities of their magnitudes.
Velocity can't be greater than speed.
Yeah. So speed, on average for a given motion, is going to always be greater than or equal to the velocity in average for a given motion. And think about it logically. Speed is always going to involve adding positive distances to the numerator, which is always going to make this numerator larger, even if I do this, and then go back again, right? Speed is all those distances summed together, so that's going to be a positive quantity. Whereas velocity, when I move right and left, I'm canceling out my displacements I just made. So velocity, because it's a vector quantity, is going to involve negative and positive motion, which cancel each other out if I change direction. Speed does not. If I change direction with speed, I just keep adding on distance over and over. So I can do this all day long and keep walking back and forth, and I keep accruing distance. Right? I keep accruing distance. But eventually, if I stop here, what's my displacement? If I started here? 0. So my average velocity, if I do that all day long, is 0. Yet my speed is the distances summed together I just did over time. So again, speed will be greater than or equal to velocity. Average speed, okay? A good theory to understand here. Oh, very good. So that's really the gist of section 2.1. I want to do one problem together, and then we're going to jump right into 2.2. Okay, is that fair? Everybody agree? All right, as long as I don't want to jump too fast, but at the same time, I don't want to make this a repetition of physics, right? This should be AP physics, not you're doing physics all over again. So let's look at an example problem. And in this example, I want to take a look at it in several different perspectives. I want to look at it algebraically, verbally, graphically, and numerically. Those are going to be our 4 methods that we talked about already, right? Algebraically, graphically, verbally, and numerically. So I'm going to dictate for a moment. I wonder if there's a way that I don't have to, I could probably do this on here, right? With Siri, I could talk to text and just have the palm appear. I didn't write it ahead of time. Here we go. Let's see if this works. You guys can see that maybe? All right. Let's see if this works. Well, huh? Right? Except it's really small font, sorry. Can I select all this fonts?
You need to talk bigger so
Talk louder and it gets bigger? There's got to be a way to do this. Hold on. There's an option for font size. Oh, there we go. Select all. There we go.
It's a NASCAR.
Tell me now, bigger, right? Hold on. Okay. All right, so that's the problem itself. Let's go through the 4 parts of the problem now. Let me add the text to the end of this problem. Hold on. All right. Can I add the next line? Oh, there we go. Okay. So part A, let's see. And this goes in 4 different parts here. As D. You guys could start, by the way, answering these as I do it. We'll go over them, obviously, together, and we'll go through it together. But if you don't want to wait while I'm typing it in, you could start answering. Can't tell where this guy, what is happening here. And D. Did that work?
Are you moving in the positive direction?
Hang on one second. Sorry. I will answer your question. Let me just fix this. Put off the screen. There we go. Sorry, Spence. Are we moving in the positive direction? So the truck. Let's see. It breaks down. It says right. Okay. So the truck runs out of gasoline. You walk along a straight road. Again, we're assuming motion in one dimension right now. So you walk along a straight road to the gas station. You walk back along the same straight road. No shortcuts, no meandering through the woods. Just, in case you're thinking about it. All right, let's take a look. Let's take a look at how to go through this. And by the way, I know this is not spelled right. It's just talk to text, so ignore any typos, please. Bear with me. So, in the beginning, we're seeing that we're driving. We then walk for a while. We want to know what the overall displacement is. So the first part seems really easy because it's just displacement, but we're not given our distances. We're given a rate and a time in the beginning. We're given a distance and a rate in the beginning. We're then given a time and a distance there. So what is part A going to be? What is part A going to be? Your overall displacement in this beginning part? Yeah. So we're just simply adding together those two quantities. Again, you drive 8.4 kilometers, and then you walk another 2 kilometers. Therefore, you go a total of 10.4 kilometers. Okay? Now, if the problem had stated that the gas station was behind you and you saw it on the way past, how would this answer change? If it stated you drove past the gas station, ran out of gas, and then had to walk back to the gas station, how would this answer change? Good. It'd be 8.4 minus 2, because you walk back 2 miles or kilometers, so it would have been 6.4 kilometers. Now, whether you drive this way and then walk in either direction, the distance would still have been 10.4. Because I go 8.4 with another 2, or 8.4 with another 2, like distance traveled is not going to be the negative vector. It's going to be positive 8.4 plus a positive 2, even if I come back, like distance traveled. Okay? Any questions on part A? All right, part B. We're trying to figure, I don't have it on my screen, believe it or not, it cuts off the line, it's different. What is the time interval from the beginning of your drive to the arrival at your station? Well, you know the 30-minute walk is 30 minutes, right? That's easy. So what is it really asking you to find?
The time that you were driving.
The time you were driving in the beginning. you've got a rate, you've got a distance, or in this case a displacement, so you can find it very easily. So let's think about this. So for part A, we can use this formula. Again, average velocity equals your displacement over your time period. We know the time period, we know the displacement and we know the average velocity. We need to find time period. You need to be able to be comfortably moving variables around in any formula. Okay, comfortably moving any variables around. Always switch diagonally. We know that one by now. You can always switch diagonally, multiply up, divide through. So our time period for driving is going to be the first thing that we're figuring out here. Time period for driving. So our displacement in the beginning is 8.4 kilometers. And our rate is 70 kilometers per hour. Now, if that's the case, do I need to convert to meters? Didn't we always convert last year everything to meters, right? We always did everything in meters to be safe. Do I have to do it here? No. Again, if I wanted to, I could. I can convert this to meters per second. I can convert this to meters and get an answer in seconds. But does an answer in seconds make sense here? No. Because we walked for 30 minutes already, right? So if I get an answer in seconds, I'm probably going to convert that back to minutes anyway. So why not just give me an answer in hours and then convert hours to minutes, right? So although it is very useful to always put everything in meters and seconds and regular honors physics, in AP Physics, you need to be able to recognize when you don't need to do that. And here, we'll notice kilometers are given, kilometers per hours are given, so my time answer will be in hours. There's absolutely no reason to convert these units at all. Chip, 8.4 over 70? I'll show you with the calculator, that's why I asked Chip.
0.12.
Thank you. And that's going to be hours. Okay, in hours. So that's the time it takes to drive in the beginning. 0.12 hours. And then what are we adding that to? 30 minutes, which is how much an hour? 0.5. So my answer is 0.62 hours.
Is a distance a capital D or
Lowercase d. Capital D, actually, that's a good question. Capital D is, I think, like the fraction gradient for E and M, the distance between the plates for the fraction. Sometimes also for density, but in physics for density, we're going to use rho. All right, so our total time is 0.62 hours. Very good. Can we convert that to minutes? Sure, we can. We just multiply by 60. Okay? If this is in hours, multiply by 60 minutes over 1 hour. Are we all comfortable with all of our conversions? Are we all comfortable? Yeah? If, when in doubt, please ask me. So if you're not sure and I just say something real quick, if the conversion doesn't make sense, please ask and I'll show it. But for the sake of this course, I'm not going to show conversions every time. Let's take a look at part C. What is your average velocity from the beginning of your drive to your arrival at the station? For this answer, find this answer both numerically and graphically. And then finally, what is your average velocity? Okay, did it go twice? Oh yeah, you repeated it twice. Why did that do that? To talk to it was working really well. Okay. Anyway, I could cross off, I guess, from here on, right? It repeated it twice for some reason.
Repeated 3 times.
I don't know. Just, yeah.
Oh no.
No, just twice. Yeah. But this is the exact same thing as that. Anyway, it's a cool feature though. This works out pretty well, especially for me for future references to know that. All right. So for part C, we want to know average velocity. We want to get the answer in 2 different ways: numerically and graphically. Numerically and graphically. So numerically first, we can use our values, use our equations. So let's go ahead and do that. So if I want average velocity, what do I need to look for in general? If I want average velocity, what do I have to look for in general? The object's total what? Displacement. Very good. Over the time period total. Okay, over the time period total. Well, the question becomes, what's the total displacement? We have that. We have that answer. Where's that answer? Yeah, part A. And get used to this, by the way. Your answers from A affect B and C and D. We're going to do this all year long, and I'm going to purposely make your problems have multiple parts. because when you get to the exam at the end of the year, multiple choice, sure, those are pretty one-step problems for the most part. But the long answer, there's 3 of them at the end of the exam, are all going to have 3, 4, 5, 6 parts to them, where part A affects B, which affects C, etc., etc. Okay? So our answer for displacement is 10.4. That goes in the numerator for there. And that came from part A. And our total time, where do we get that? Yeah, part B. So the book is slowly stepping you through this idea. Okay, this idea of using your previous answers to get your next answer. Let me put some dividers up so it's clear. Okay, so we got part A, part B, and now we're on part C over here. So we get an answer for average velocity. What does that come out to be? Around?
16.7.
So 16 point, let's say 8 for now, that works. By the way, I might start writing V bar like I did last year in my course. I know it's not a common nomenclature in this book, but I hate writing V av every time. AVG every time. A bar over the top can indicate either average or can indicate a constant velocity. So it can be misleading. So I'll keep writing this, but as soon as you start changing to a bar, just recognize that. So that's my average velocity, and I've computed that numerically. Using numbers, right? Using numbers. We're not doing things algebraically here because we're given numbers. If we were only given variables in this problem, and our solution was like x equals v plus nu over x squared or y squared, that would be an algebraic solution. We're getting numerical solutions right now. We're using numbers. But if I want to do this graphically now, how could I show this motion graphically? Can somebody step me through the process of showing what happened graphically here? I'm going to kind of start making it smaller. I know it's really small now, sorry. And I'm going to do it over here on the right. I'm only going to put the first quadrant. Yeah, Tristan, again.
Position versus time graph.
I like it. So position and time. And give me some important position moments, Tristan.
You know 10.4 kilometers, that's actually the displacement, so that would be what the x value
So at the end, I know I'm going to end up at 10.4. So I'm going to put a marking on my graph already. I like that.
and then on the bottom you put 0.62.
And I know that it's going to end at 0.62. I like that. Good. Now, it's not going to be a straight line now. We know that. Our average velocity will be a straight line. If I wanted to graph the motion, I did not walk or drive or move at the same pace the whole time. So I need to make what kind of a function here that has parts to it? What do we call that in math?
Piecewise.
Piecewise. So somebody else now, tell me what this piecewise function will look like. God bless you, Matt.
It would be a straight line from.
All lines are straight. Keep going. If you said curve, then it's different. All lines are straight, but give me more then. Don't use the word straight line.
It would be a linear function from
Go ahead.
the origin to 8.4.
Comma.
8.4 and
How much time elapsed in the beginning?
0.12.
Very good. So those are my key points. So Tristan gave us the ending points, which are the most important for our answer. But when we graph this motion, we can't just connect the two because that's not the actual motion. The motion in this problem is segmented, truncated, pieced together. So we put our next point at 0.12, 8.4, and then as Tristan said, the last point over there. And that would show us our motion really. And I can connect. I can connect from A to B, and then from B to C. And yes, as Matt said, it is straight line motion here, or it is linear motion. We are not accelerating. We have nothing to do with acceleration. Therefore, the velocity that we exhibited was constant within each piece of the function. What was the velocity in the first piece of the function? What was the velocity in the first piece, Max?
70 kilometers per hour.
What was the velocity in the second piece of the function? Did we ever calculate that actually? Did we calculate that? We didn't, but you can calculate it real quick.
4 kilometers an hour.
Good. How did you get it? Good. He recognized you're walking 2 kilometers in a half an hour in the second part. Remember, you drive, you run out of gas, you then walk 2 kilometers in a half hour, which is 4 kilometers in every hour. That's the slope of the second line. Why is the second line a lower slope? Because you're walking. Because you're walking, right? Clearly? All right. Now notice this graph may not be drawn to scale. I tried my best to make it look like it's the scale, but I don't care. Don't care. Because I know that you guys know your math. If I was teaching this to a freshman math course, it would really make a point to draw the scale. So they could see the significance of 70 as a slope versus 4. But you guys recognize what I mean here, right? 70 is a very steep slope compared to 4. So the scale is not perfect here. Now, again, that gives me my motion. If I wanted to calculate, though, the average velocity from beginning to end, from our lab, what line do we use for average velocity? What line do we call it? Sure, the vector from tip to tail works, but what's the name of that we called it? The secant line. So yes, from tip to tail is what we're looking at, the resultant, or the secant line. So connecting those 2 points and finding the slope of that line, what do we get for the slope of that line? I like that Max didn't even touch his calculator. Max, what's the answer? Good. We don't have to do any work, guys. It's the answer we just got, right? Remember, it's the average velocity. It's this number right here. There was no work necessary for that to come. Now, we can verify graphically that the slope of this is definitely 16.8 kilometers per hour by doing 10.4 divided by 0.62. But we did it already. It's right here. So we could absolutely calculate the slope of the yellow line by finding y2 minus y1 over x2 minus x1. But there's no necessity here. We're just showing it graphically. Any questions on the graphical representation of this motion? We're good? Awesome. Part D?
Alright.
Yeah, go.
So that's essentially just vector addition, right?
Yeah, that's actually what that is. That would be the vectors that you're summing together, giving you the overall resultant. Yep. And that resultant, if you recall, this resultant here is really representing both position and time. Position and time. Yeah. But we don't really need to think of it as vectors here because it's not as necessary. But yeah, you can think of it that way, absolutely. Good idea there, good idea. All right, part D says, suppose that to pump the gasoline and pay for it and walk back to the truck, it takes you another 45 minutes. Back to the truck, 45 minutes. What is your average speed from the beginning of the drive to the return to the truck with gasoline? You got a question or you want to impose it?
Kind of both.
Good.
So, over that 45 minutes, does he still walk at the same pace that he walked before?
You have to make that assumption because it's not given, and we're told that he does walk at a pace of, well, no, he doesn't. Sorry, no, I apologize. It's 2 kilometers back, and it's 45 minutes.
Right.
So you can figure out the pace.
Right.
Well, you said
But
that
like
he's pumping gas, so he just
Sorry. Say
pumping
again.
gas and paying, so you could probably
True, he is going gas and paying.
You could say
I think.
that's like 15 minutes.
So actually, let me ask this question. Sorry. Do we need to know his average rate?
No.
That's the answer. I apologize. You do not need to know his or her, whoever it may be, average rate on the walk back. Because we're not being asked to find the average speed or velocity on the walk back. We're trying to find the average speed for the entire trip beginning to end. Okay? It's a really good question. So we don't need the speed on the way back or the velocity on the way back. Londell.
So would you add 2 kilometers to 10.4 to the total distance?
So if we want speed, we get distance over time. So Londell said, yeah, we have the distance traveled earlier was 10.4, and that was all in one motion or one direction. We then turn back and go another 2 kilometers to come back. How much time has elapsed for this entire trip, Chip? Give me the numbers to add together, not the total answer.
Okay, 0.62 and then 0.7.
Very good. Where's the 0.75 coming from, Chip?
3/4 of an hour.
So, you walk or you move a total of 10.4, and we did that in 0.62 hours, right? That was this number. Without this is the same answer as earlier. But we walk another 2 kilometers in another 45 minutes. 45 minutes being 0.75. So the total distance is this over the total time. What do we get for an average speed for this object, person, combination, whatever? What do we get?
9.05.
9.05.
And the speed here can be less than the velocity of the other one during a different time frame, right?
Well, let's talk about that. We didn't get the velocity yet for the whole trip. We only got the velocity for the beginning.
I'm comparing the velocity to the beginning.
Yes, very good. So notice what Spence just said. The speed for the entire trip is lower than the velocity in the beginning. But the velocity for the whole trip will not hold true. Let's figure out the velocity for the whole trip right below. What would the velocity be for the whole trip? How would I compute it, tell me? Don't give me an answer, but tell me how I would compute it first. Lundell, what do we do here?
You'd subtract 2 kilometers from the tempo.
Very good. And that's the only difference here, because our times are always positive quantities summed together. But if I wanted speed, I'd be going 10.4 this way, and then 2 back to my car, which really only yields 8.4 in the numerator. So we've got 8.4 now divided by that quantity. What does that give me?
6.13.
There we go. So we can see, as Emily stated, Emily was here, right? That our average speed for a whole trip, I'm going to specify that, for a whole trip, the average speed will always be greater than or equal to the average velocity. Okay? Always. Now, if I didn't change direction, as Spence said earlier, these numbers will be the same. If I didn't change direction, these numbers are the same. Now,
What is the 0.75?
that's the time it took you to walk back to your car and pump gas and do all that. So I'm taking away 2 kilometers because you're going back to the car, and that whole time takes 0.75 hours. Here I added it because I'm thinking of this as a distance. Here is a displacement. Okay? Yep. We good on this one? Okay? Awesome. So, where would you see a problem like this on an AP exam? Part 1, multiple choice. So not be a part 2 problem. Too easy for part 2. Write that down, okay? When we do problems, I want you to start recognizing where they'd be useful. This will definitely be a kind of multiple choice problem. And you could have problems 6, 7, and 8 with several parts with one scenario. Which we'll do on the test. It'll say, use the given diagram, or use the given scenario for problems 7, 8, and 9, which could have multiple parts. But this would be too easy for a long answer problem on this exam. Okay? It'd be too easy for a long answer problem. All right. Let me think for a second. Yeah, I want to at least get into some calculus today, so let's get into 2.2 here. So in 2.2, we're going to take a look at what's called instantaneous velocity and speed. By the way, I'm going right out of Halliday for these notes when I say 2.1 and 2.2. So I might not be writing at the top, but just if you want to denote that this is now section 2.2. So let's talk about instantaneous velocity and instantaneous speed. So we could look at this formula first, and we could say, well, in the last chapter we said this. Or in the last section, I should say. We said that, right? An average velocity equals our displacement over our time period. Now, if I wanted to figure out the velocity at a given moment, how long is my time period? Very good. 0. At a given moment. At this instant in time, what's my speed? What's my velocity? Well, if it's at an instant in time, how much time has elapsed? 0 seconds. But I can't divide by 0, right? We all know that becomes
0.
undefined. Undefined. Now, because of that, I cannot mathematically use this equation. I just can't do it. So what do I do in calculus? When I want to find, as the denominator gets closer and closer to 0, what do I use? Good. Which is, how do I get a derivative? By using a? What's the word we use to get derivatives? The blank process? The limit process. Very good. So we want to take the limit as delta t goes to 0. Remember in your math course, you did the limit as h goes to 0, right? Did you do h or delta x? What do you guys do? Delta x? Sorry. So you're doing f of x plus delta x minus f of x all over delta x? Good. So instead of delta x now, it's delta t. Pretty much, it's the denominator used to go to 0, right? Same concept. Same concept. So the limit as delta t goes to 0 of this idea, of this. Now, what does that yield? That yields the velocity at a given moment. So notice now I'm not putting a bar over the top. I'm not putting average down here anymore. When you see v by itself, the assumption is it's the velocity at a moment. Initial, final, somewhere in the middle, but at a moment it's the velocity. So when you see v by itself, it automatically means instantaneous velocity. If I wanted to know the average velocity, I would put a bar or the word or the letters AVG as a subscript there. Now, in your calculus course, you've learned this as the derivative. So we could say this equals dx dt. Now, dx simply means the derivative of the position with respect to time. You might, if you use this, this symbol, dx dt, okay. Keep me posted so I know where you're at.
Yeah, but not by hand, but
On the calculator,
He
you see it.
varies, he likes to vary it, so we're used to seeing.
Good. You see f prime of x versus dx or d by dx? Good. And that's what you're going to see a lot of here also. So I could write this instead of dx dt. I could say that velocity is really x prime of t. It's the position function, but its derivative at a given time. So in words, if you want to write this down, because I found that when I was taking this course, writing out these in words helped me a lot when I was studying. So I would write this as the derivative of position with respect to time. That's what dt means, with respect to time. Over here, it's the same thing. It means the position first derivative, or x prime is the way you'd say this. So x prime of t, or dx dt, mean the same thing. They mean, again, the derivative of position with respect to time, aka instantaneous velocity. Now, how about speed? What if I want the instantaneous speed? What if I want the instantaneous speed? Good. Now here, you absolutely take the absolute value, and only that. Because remember, earlier, think back to earlier with average speed. Average speed included several segments along the way for a given time period, where your displacement was positive, then it could be negative, agreed? Whereas here, when you look at instantaneous speed, it's at the moment. So, let's do a freeze frame. Okay, the track star is running, and you freeze frame. So here's the track star, running at, what's a good speed for track stars?
120.
Odell Beckham Jr. is speaking around like 22 miles per hour top speed. It's crazy. Let's say track star runs like 21 miles an hour. Okay? So they're running at 21 miles an hour positive. That's their speed at this moment. My velocity at that moment. My speed is the same thing. But if the track star is running this way, the instantaneous velocity is negative 21 miles an hour. But the speed instantaneously is 21 miles an hour. So as Spence said, if you want the speed, it is definitely going to be the absolute value of the velocity. And we're talking about instantaneous speed here, not average speed. Remember, average speed is distance over time. We're going to use that formula from the last section. But here it's just the absolute value of this quantity. So you could write it that way. You could write it as this. You could write it as, this. Okay, any of those definitions are fine. Because velocity are these things anyway. So if I want the absolute value of velocity, take the absolute value of those things. Okay? Alright. Very good, very good. Let's take a look at a graph of this. Let's take a look at a graph of this so we can get an idea. Can I go on to the next slide? Anybody writing still? Okay, I'm going to go on then. I kind of want to squeeze everything in here. So I'm going to draw a graph. I want you guys to copy my graph down, please. And what I want you to do is, I want you to put two successive graphs below this. Anybody want to guess what I'm doing with this idea here? Why am I putting three graphs? Anyone have any suspicion? Max?
You like graphs?
I'm going to give you a hard time because I know you took calculus.
Yeah.
Why would I put three graphs, Max, in a position problem? And then, which is really the The derivative of position is the,
Velocity.
and why would I put another graph next? Tell everybody.
Acceleration.
So we're going to talk now about acceleration also. Acceleration is the derivative of velocity. You're going to learn this in math and calc in probably a month or two. But why not do it now, right?
It's the derivative of the derivative.
Oh, very good. We call that the second derivative.
That's
It's
great.
not, it sounds crazy, but it's no more difficult than taking the first derivative. You just get your answer for the first derivative and you do it again. It's not hard. You can take infinitely many derivatives.
What would be the point of that?
What would be the point of it?
Yeah. I mean, like, besides like the cast be like second or third.
Yeah. After the second or third, it's not much point actually. The third derivative is called jerk. The fourth derivative is called snap. The fifth derivative is called crackle. The sixth derivative is called pop. They actually did this a long time ago. I looked this up like last year because I was like, what do they call these other things? I mean, the idea is like,
Jerk, snap, crackle.
yeah, it might be actually like jerk, twinge, snap, crackle, pop, or something. There's another one I think in there somewhere. You can look this up actually and figure out what they are. It doesn't matter though, obviously. But after the second derivative in physics, there's not as much significance to it. Okay? It'd be an acceleration of an acceleration, or like a rate of change of an acceleration is what it would be. Imagine a rocket leaving space. So a rocket is accelerating on the way up. But if the rocket thrusts with more force means more acceleration. So your acceleration can change. So the best example of the derivative of acceleration, which is jerk, would be a rocket leaving the atmosphere. Because it actually accelerates at different rates as it's leaving. So that would be an example of that. Anyway, let's get to the point of the problem.
Jerk, like J-E-R-K.
Yeah, the word jerk, yeah. Like you're a jerk, yep.
Never thought anyone would know.
Right? It's what they chose as names, I don't know. All right, so let's draw this graph, please. So let's start with our position graph. Try to draw it as close to mine as possible, please. Not putting numbers. Not putting numbers. Now, the way I have you draw the other two graphs are directly below the first graph. And the reason I do this is because the time periods should all correspond to each other. So the important parts of our position graph should correspond directly below with our velocity and acceleration. So tell me in words what is happening to this particle, object, motion, whatever you call this, from the first graph. Tell me in words what is happening. First in words. Tristan, go ahead.
It starts out slowly, then it accelerates a lot, and then it slows down again.
Slowly moving, if that even, right? It's practically not moving at first, we could say, because it's pretty much zero slope. So not moving, slowly moving, then you said accelerates, very good.
And then it slows to a stop.
So wait, first it accelerates, it then moves at a constant speed in the middle for a little bit, because you see the slope in the middle is constant right here. See what I'm saying?
Oh, yeah.
So then it has a constant velocity, then it slows down, and then it stops. So there's a lot going on. So let's use a color coding system to show this. So the constant velocity will be a black line. Not moving are going to be red lines. Slowly moving, I'll use green. And then yellow I'll use accelerating and decelerating, which is speeding up and slowing down. Okay? So what am I referring to in this whole problem? What am I looking at? I'm looking at the slope of the position time graph. Specifically, not the secant line, but the tangent line. Okay? And if it's not clear, let's do it together. So, here we go. Slope in the beginning is approximately. So the velocity in the beginning is 0. Remember, velocity is the slope of this graph. Then, in the yellow region, we've got a very, very, very low steepness of our slope. So we've got a slowly moving object. Then, watch the ruler. It starts to curl like this, and the derivative of the tangent gets steeper and steeper. That's the acceleration portion. Then where it's black, look, it's a linear function there. It is a linear function. Because the derivative, or the tangent line, at any moment along the black line here, is the same slope. So it is a constant velocity, because the slope doesn't change in the black region. Then, in the yellow region, we see that the slope gets lesser and lesser and lesser, so it is slowing down. The velocity is getting lesser and lesser. And then finally, the red at the very end is a flat red line, and it's too short to reach it, so it's a flat red line like this. Therefore, it's flat, no slope or no velocity. It stops at the end. Chip.
I was gonna ask if you feel like a car, like quickly accelerating to a constant speed and then just stopping like a 0 to 60.
Perfect. That's exactly right. A car literally accelerating real quick, reaching the speed it wants to, staying there for a moment, and then a red light, slam on the brakes. How many of you ever seen Meet the Parents? It's an older movie. It's so funny if you haven't seen it, by the way. It's with Ben Stiller. Do you remember the scene when he and Robert De Niro are racing to get home because the cat did all that craziness and damage? And every time they hit a light, it turns green, he nails the gas, and then the next light is red, and they have to like screech to a halt. That's this. He picks up speed, gets to his speed for a moment. Well, he probably doesn't coast ever, right, in the middle there, but then has to slam on the brakes afterward. That's what you would see here. Good idea there. We're thinking about a car. All right, so those are our regions. Those are our regions of displacement. How can we draw the graph of velocity then? What we can do is we can use our words on the right to help us. So, using our words on the right, let's create a velocity time graph. So what's the velocity in the beginning? In the red region, what's the velocity? 0. By the way, I'm going to use, let's see, for this whole graph, I'll use a new color. Let's use gray. So in the beginning, the velocity is definitely 0. So I'm going to continue that gray line until it corresponds to the dotted line that I make to correspond with it. See what I'm doing here? See why I put the dotted lines down? See why I put the velocity graph directly below? You guys are learning so much now that you're going to do in calc. You're not going to do this in calc until the end of chapter 3. In your text, it's the end of chapter 3 in that, but we're doing it now.
Is that a line in between the red and the red with the equals to t graph?
This here? Yeah. So that's a flat line showing 0 velocity in gray. Yep. Okay. Then what happens? What happens in the green to yellow region? What happens? Because green and yellow are kind of together, right? We're going to group these. This is the first region. These two are really kind of together. What's happening in the green and yellow region in general? What's happening to the velocity of the object? The velocity is increasing. That's what the word acceleration means, right? So, all you got to do, and I don't care how high you go in this, all I care about is that until you get to the black region, I should use black the whole way down with the dotted lines. Go ahead and draw a dotted line region again. So in this region, I want to see an increase in velocity. I don't care how high you go for the velocity, you've got to show an increase.
Would it be linear?
It would, because we didn't know if the acceleration is changing too much. So we have to assume that it is increasing at a linear rate for now. We'd have to know more about the problem, Spence, to know if that would be a velocity that's increasing with some slope to the velocity or not. Good question. Very good question. Now, in the next region, in the black region above, let's go ahead and talk about what happens there. So we're now in this region. What kind of velocity is it? We have the words written for us. Jim?
It's constant, so it's going to be another,
Thank you. A horizontal line. You're going to say flat line? That's fine. A flat line or a horizontal line in that region. Because again, the velocity is constant and we're graphing velocity, so I need to graph a constant line. And a constant function is a horizontal line from your Algebra 2 pre-calc course. Then, in the next yellow region, let's go ahead and draw another dotted line. Bridge, what happens in the next region in yellow here, if I'm on my...
Slows down, so the line's going to go diagonally down.
Very good. And eventually, what does it do, Bridge, at the end?
It stops, so it's just like a flat line.
I like it. So I'm going to have to do this. Take a look. It's got to go back down to the horizontal axis. It has to. Because in the red region, what's the velocity, everybody? In the red region, it's 0. So there's no way I can come to here. Take a look where I'm pointing, please. There's no way you can draw this line to here and then drop it down. It's not going to work. You can't have velocity one moment and the next moment not. You have to actually gradually slow down. Sorry, so what I said is kind of not true, right? Your velocity could be like 0.000001 and then 0. What I'm saying is you can't have a lot of velocity one moment and then stop in this circumstance. What would that exhibit? What would you have to be physically doing for you to be moving, and then just stop?
Hitting something.
You have to be hitting an object. You have to be crashing into an object, right? To have velocity and a hit. But even in that circumstance, you would still see a steep line going down to connect to the axis. So yes, here we know that it's stopped in the red region. So that's going to be, again, 0 velocity. So there's my velocity graph. There's my velocity graph. Okay? Now, can we draw the acceleration graph? Becomes the next question. We should probably bring down those dotted lines, right? It seems like those are important. So let's do that first. In your calc course, when you have numbers, and here when you have numbers, you're just designating the numbers on the x-axis, on the horizontal axis here. Okay? You would just designate tick marks at those locations. I'm using dotted lines because we didn't use numbers here. Can somebody tell me about the acceleration here?
1 minute.
Come on, 1 minute. 1 minute, Max, go.
No acceleration
No acceleration. When, Max?
from to the first level.
Yeah, and that makes sense because is the object moving in the beginning? So Max knows already that the acceleration has to be 0 there. And what about at the very end, Max?
0.
Yeah, so let's do that already. Fill them in. It's got to be 0 acceleration. Now, what did we say acceleration is the derivative of?
Velocity.
So really, it's the slope of the velocity graph. So can't you just find the slopes here? What's the slope here? Everybody, what's the slope right here? Because it wasn't in a constant velocity. And when you have a constant velocity, what's your acceleration? 0. So the middle region, we know also is going to have 0 acceleration. But we have positive acceleration here, and we're going to have negative acceleration here. Speeding up, and then slowing down. So there's my acceleration graph. I can continue this tomorrow with a little bit more of a tidbit or a little bit more of an explanation. Tonight I'm going to give you homework, okay? I'm not going to assign it this moment. Today's Thursday. I don't see you guys till Monday. So you're going to expect a little bit of vector homework from the multiple choice sets, and then most likely some multiple choice and some math problems out of 2-1 and 2-2. So check later today on Moodle. I'm going to be assigning it and try to keep up with you guys. If you don't see it later and you're wondering, feel free to email me and I'll make sure to put it up.
Okay. Are those vertical lines or are they slanted?
Yeah, that's what I
Technically, these are slanted. Technically, they have some slant, but they're going to look like vertical lines. But technically, they have some slanting occurring there. We'll get into that next class, actually. That's a good question.
Thank you.
Guys, have a great day. Good job today with this class. I'll see you all on Monday. It's tough to say that, when you have class tomorrow still. You're welcome.
It's a good job.
It is. I actually like it. Do you like it better?
Just do some work there.
Right? And then you have 2 days to really let it ruminate, let it sink in, let yourself do homework.